Hello, my name is Kevin Shabahang. I'm a PhD candidate at the University of Melbourne and will present some explorations of associative nets I carried out with the help of Professor Simon Dennis and Dr. Hyung-Wook Yim. Neural nets trained through backpropagation have been making great strides in the wider AI community, but people don't require nearly as many examples to learn. Here we aim to revive a class of neural nets that were abandoned due to their difficulty with generalization, but are more plausible models of human memory. An associative net is characterized by a state vector, a weight matrix, and a time update function. The state vector captures the activation of a set of hypothetical neurons, and the weight matrix represents the synaptic strengths connecting the neurons. Encoding is Hebbian, where synapses between neurons that are active within a time interval strengthen. It's implemented by taking the outer product of a trace vector with itself and summing the result into a weight matrix. The weight matrix can be decomposed into a set of orthogonal axes or eigenvectors, each with a corresponding eigenvalue whose magnitude increases the more variance that eigenvector captures in the encoded traces. Retrieval is driven by a time update function, where the state vector is first initialized to a probe and is then multiplied with the weight matrix to give the state at the next time point. This process is continued iteratively until the state vector stops changing. The final pattern is called a steady or equilibrium state and is taken as the retrieved response. The simplest update function is linear, where the next state is the unit normalized vector multiplication of the current state vector and the weight matrix. In the limit, the linear associative net always settles to a single vector corresponding to the dimension capturing maximum variance in the encoded traces, the dominant eigenvector. Anderson, Ritz, and Jones introduced saturation in the brain state in a box to remedy the dominant eigenvector problem by constraining different states to lie within a box. They did this by imposing an upper and lower bound on the state vector activations. Although saturation solves the dominant eigenvector problem, the BSB is still limited because its equilibria are restricted to previously encoded traces. We present dynamic eigennets as a novel class of associative nets with greater promise for generalization. Dynamic eigennets incorporate short-term plasticity by temporarily summing the outer product of an input into the weight matrix prior to retrieval, whereas the weights combining the eigenvectors or their eigenvalues remain static in the linear associative net, and the BSB, short-term plasticity, weights each eigenvector in proportion to its similarity with the initial probe. We constructed a bigram dynamic eigennet and trained it on a large text corpus. We then sampled a set of bigrams, introduced a syntactic violation, and then probed the system with either the valid or invalid bigram. We used the vector length of the final state vector prior to normalizing as a measure of familiarity. Finally, we subtracted the familiarity for each invalid bigram from the corresponding valid bigram. We did this for 9 different bigram types with 150 samples for each bigram pair. We then take the difference scores for each bigram type, take its mean, and divide by its standard deviation to get a measure of discriminability. Each row of the following table shows results corresponding to one of the 9 bigram types. Valid bigrams are shown in blue and invalid bigrams are shown in red. The second column shows some examples, and the third column shows the discriminability when memory for the valid bigram is intact. In a fourth column, we show the discriminability for the bigram violations when we lesion memory for the valid bigram prior to probing the system. Higher discriminability here indicates the model's capacity to generalize from the eigenstructure encoded in the weight matrix. In conclusion, augmenting linear associative nets with short-term plasticity appears to make them more conducive to generalization. Associative nets fell out of favor with the rise of layered backpropagation networks. However, backprop nets are far slower than people. They are incapable of one-shot learning. Hebbian systems remain a more neurally plausible alternative. I end this talk with the conjecture that perhaps human generalization results from recurrence in an STP-augmented associative network as opposed to slow error-driven learning. Thank you.